All right, hello everyone. So we are entering into a new unit. It is a little unfortunate. We are entering into this unit with me not really being there, but I think we will be okay because you're going to do a couple of labs in class and a couple of practices on your own. Unit 6 is also a very exciting unit because it really kind of starts to tie up a lot of loose ends, I like to say. So in unit 3, which was the vocab unit, we learned a lot about all these different vocab words. And the whole point of kind of doing it at that time was because we are about to use a lot of those vocab words in examples. So it's good to kind of see the black and white definition of them and then get to see kind of what they mean mathematically. The other thing is in the last unit, we were doing a lot of this like, hey, I have this sample. How weird is this sample? Should I be alarmed about this sample? And we're going to be kind of taking that concept into something we call a confidence interval. And confidence intervals, in a very rough introduction sense, is this idea of saying like, hey, this is the mean that I got. I ran a sample. This is the mean that I got. From that mean, then, how much wiggle room is there if I was to try to be predicting the population? Because again, it's very easy to get a sample, but it's not usually very common to see the population. So if I was kind of curious about how many hours of sleep somebody gets, it might be very doable to find a sample and find the average for that sample, but to take that and find the population's sleeping habits would be very hard to do for the entire world, right? So populations just really are not ideal to find most of the time. So we operate a lot in samples. I mean, the whole world of, research and studies and stuff like that exist in the world of samples. So again, confidence intervals is this idea of I can absolutely find the sample, but then how can I use that sample to make a prediction about the population? So let's get into this PowerPoint a little bit. There you go. Okay, so up first, you can kind of see at the top, it says it allows us to estimate the population parameters. So very similar to what I was just saying is we're going to be using samples to make predictions, or they use the word here, estimate, for these population parameters. And remember the difference between a parameter and statistic when we are doing our vocab unit. So obviously we're kind of using statistics to make a prediction about the population parameters. Yeah. So moving into the estimators. So you have this idea of this point estimate. The point estimate is technically like your X bar, and the X bar should not be mistaken with, going back, to the last unit. X bar is different and is usually a different number than mu of X and mu of X bar. So mu of X and mu of X bar, like when you think back to that formula that we had previous, it was X bar minus mu of X bar over sigma of X bar. And I'm going to be attempting a little bit of switching between my screens a little, because sometimes I want to be able to write on them. So bear with me here. But when we are in the last unit, we had this idea of X bar minus mu of X bar over sigma of X bar. So it should be noted that X bar is different than mu of X bar. Mu of X bar, or you can take that even further and say mu of X. Mu of X was from the population. X bar is from the sample. So what we're going to be focusing in on this unit is really the X bar and kind of how the X bar, how good of a predictor X bar is. Then we come in here and it's the interval estimates. So the point estimate is exactly that. It's usually a single point, like, hey, this is my sample, this is what I got. The interval estimate kind of takes us to the next level and kind of says, yes, I found my point estimate, but I'm going to take that point estimate and kind of branch from it. So take a look at these two examples here. What you're seeing here is ultimately what we call the point estimate. So that was from my sample. This is the value I got from my sample. And then we add or subtract something that we'll talk in the next slide that is called the margin of error. And what this does is it creates an interval, because again, plus or minus, it creates an interval that we can then kind of use as our predictor. So what I can do is I can take that 165.7 plus 18.2. I can also do 165.7 minus 18.2. And what that does is it creates an interval for us. So I'm going to go ahead and put that interval down here. So we would be anywhere between the numbers, oops, write the smaller one first, 147.5 to 183.9. And we can run the second one too. The second one should work out to be a 2.75 to 5.75. But ultimately, point being here is that we are creating a little bit of an interval in a sense. So talking a little bit more specifically about these confident intervals that we have going on here. So with these confident intervals, as I said before, we usually have our point estimator, which is kind of a set in stone. This is what I got from my mean, or from my sample, I should say. And then I'm going to add or subtract a little bit of wiggle room. And this part right here, as defined, is the margin of error. Now, margin of error should really excite you because we've heard of the margin of error before. The margin of error we defined as kind of that natural phenomenon. It's nothing that we did wrong. It's just, hey, you might get a little bit lower values or a little bit higher values just from nature, in a sense. And so this 3.9 is that margin of error. It kind of says, yes, this is what I got from my sample, but if I was a little bit higher or a little bit lower, it's okay at the end of the day. You know, it's a natural phenomenon that happens. Now, interpreting this a little bit, we would go about saying, we'll talk about this 95 here in a little bit, is given in this problem, so we're just going to ignore it for now, but it says we are 95% confident that the true population mean lies between, and then we would calculate those margins. So those margins would end up being 13.58 and 21.42. Again, doing that 17.5 plus 17.5 minus gives me those two numbers. Now, a small little, actually, I'll say it in the next slide. Sorry, getting ahead of myself, getting excited. Last part, I just want to add in there. If we wanted to be more confident, so you're seeing up here, we're 95% confident. I mean, I think 95 is a pretty good number. But if you wanted to be more confident, then ultimately you're going to have to do something where you increase the interval. So let's talk about that idea of increasing the interval here. So building off that. Think of increasing your confidence level. And I think the mistake people make when thinking of confidence intervals is they think about the, let's say this, the human interpretation of confidence. So they think about like confidence in like how you feel confident. Oh, I am super confident in this, da 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 da. But confidence in statistics should not necessarily be interpreted the same way. So confidence is this idea that, hey, and I have a picture of Annette here, I am going to be, or I want to be fairly confident that these numbers that I present to the public, so pretend like you're doing a research study, these numbers that I'm presenting to the public really have to be pretty accurate, okay? They might not be perfect because it is based on a sample, and I'm kind of telling the public or the population about this study, these results. So I want to cast a net that is pretty generous and will hopefully be pretty accurate towards the population. Again, you don't know the population. So going back to the one that we just did here, when we cast it, let's think of this as net. When we cast this net of a 3.92, it's giving us this window from 13 to 21, about 13 to 21. What we're saying is that I think that in this interval, the population mean will be here, hopefully. So we're ultimately casting out this net and saying that I'm hoping that by having this window, this range here, that the true population mean will be somewhere in there. I can't guarantee it will be, but I'm trying to be super confident in that. And 95% kind of gives you that idea. So if you ever wanted to be more confident, again, think of, here's a fishing analogy for my fishing people. If you are 95% confident that I will catch a fish and I throw out this net and I'm like, okay, I'm going to catch this fish. You're not guaranteed to always catch the fish, but you're 95% confident you will. If you wanted to increase your chances of getting a fish, what would you do? You would get a bigger net, right? So if you just have a small net and you throw it out and you're like, oh, you know, I might get a fish, I'm pretty confident. A bigger net is going to increase your confidence. Now, it should be noted that confidence and precision are somewhat different concepts there. Precision is this kind of focused in idea of kind of saying, I'm going to give you the most precise answer I can. But with more precision comes a narrower interval. Like if you're trying to be as precise as possible, you're going to have a pretty narrow window. But if you have a narrow window, think about what I said before with the size of the net, a narrow window kind of reduces your confidence. So you have to, when you're looking at these two things, you really have to kind of think, do you want to be super confident or would you rather be precise? Now, in some cases, precise is a good thing and confidence doesn't matter as much. But other times, confidence is going to be very important. And if you're going to increase your confidence, you're going to decrease your precision. So it kind of almost operates under this idea that if your confidence goes up, your precision is probably going to go down. If your precision goes up, your confidence is going to go down. So you really can't increase both at the same time. If you're going to increase confidence, your precision just has to go down. Your interval is going to get bigger, which means your precision is going down. If you want precision, you know, you want to give this really small narrow, you want to be precise, then you should probably not be as confident in your answer because you're giving a very small window and you're like, haha, I'm precise. But you really shouldn't feel confident in that. So do keep in mind that precision and confidence have different meanings. You can be very precise, but if you're precise, you should preface to the audience that, you know, you're maybe not as confident in these results. You're like, hey, I'm giving you precise results, but I'm just not super confident in them. Okay. So when getting into confidence levels, now I will say precision is not something we're going to focus on as far as vocab goes. This unit is called confidence intervals. So we're going to be more focused on kind of how do we figure out these intervals? How did I actually get these numbers? So let's get into it. Now, when it comes to getting these two numbers, it should be noted that there is going to be a difference between having sample statistics and having some parameters, but I'm actually getting ahead of myself a little bit. So let me back up a second here. So here we are at the next slide, this confidence level part of things. So confidence levels, we heard earlier on the one slide where it said 95% confidence interval, and then it gave the margin of error. So confidence levels, you can ultimately a lot of times pick your confidence levels. These are your most common ones, 90, 95, 99. Obviously, there are some other ones out there. I've seen 97, and you know, your confidence level can really be anything you want. Obviously, a 99% confidence is going to be, you know, top of the line, where you're basically saying I almost have 100%. And then you got this 90% up here where you're offering yourself a little bit of space where you're saying, hey, these are pretty good odds. I'm pretty confident in these results, but at the same time, like I am only 90% confident in the results. So how do we work with this 90%? Now, if you think back, we've seen these percentages once before. If you think to when we did normal CDFs, and I would say that I want to find something we call the critical value. Here's that word again. The critical value where I get the top 10% or the lowest 10%. So if I wanted to know the critical value at 10%, right? We've done this before. This should sound familiar. I want to figure out the critical value in which the cutoff's at that lower 10 percentile. So I know that this is 10%, but based on my information, what is this critical value? And the first thing you would always need to do is find the z-score. Once you had the z-score, sorry, it's not as clear as I had hoped, but you know, it's okay. But once you have your z-score, then you would go over here to the x minus x bar over s of x, or whatever formula you were working with as far as symbols go. But you'd find that z-score, and then you'd go about ultimately a lot of times solving for x, as we called it, the critical value in a sense. Here we're going to be doing the same thing, but actually we're going to stop at the z-score and not really take it any further. So how did we go from having this 10% to a z-score? Think to yourself. Think when we did z-scores, we had this notation where we would go, oh, why am I blanking right now? We would go the value to z-score to percentage. So when you go one direction, that's normal CDF. When you go the other direction, that would be inverse norm. So what are we doing? Inverse norm. So come up to these problems now, and in short, we're doing inverse norm. So again, something we've done before, so it's somewhat familiar. I'm going to write at the bottom here, inverse norm. Okay, and so when I'm looking at this one up here, it kind of walks you through this idea of inverse norm. We would typically plug in 0.05. That gets you your negative 1.65. But if I'm looking for a 90% confidence, think where that would be on your bell curve. A 90% confidence, boop, would actually be over here. Because again, you're saying 90% exists below. So I probably don't want the negative version. I want the positive version. So this would be a 1.65. We call that your critical value. And then we go to the next ones. We got 95, 99. So again, we would do a similar concept. I'll go inverse norm. Remember, you're not actually typing in 95. You're thinking more about like how much space is in that little section. So with a 95, you're saying like 95% is in the middle. That would put 2.5% over here, 2.5% over here. Once you have those 2.5s, that's kind of what you're doing the inverse norm of. And then just keeping in mind, you want typically the positive version of that. You won't really be having too many critical values that are negative, because a negative critical value would mean your confidence level is like 10%. And you don't want to have a confidence level of 10%. So this one I will do 0.025. But again, reminder, when you get those negative values, you should make them positive. This one I'll do inverse norm. It's 99. So that's actually going to be a 0.005. Be careful with that, 2 zeros. Calculate each of these. That's going to be a 1.96. And this one will be a 2.58. Now keep in mind, these values that you just got, these 3 critical values, these are basically something we call the z-scores. And you've actually not really questioned too much about the idea of z-scores, but we're going to question that a lot more today. Now, as I progress, I do just want to preface something, guys. Informal conversation. You don't really have homework tonight, so if this video goes a little on the long side, I do apologize, but we have a lot to get through. So if you don't finish this video, just come back to it later and pick up where you left off. So back to my next point here. So we're kind of chugging through these PowerPoint slides here. And we're moving on to, okay, we just talked about z-scores, and you're like, cool, why are we talking about z-scores if we were just talking about confidence intervals? How do these two things actually relate to each other? Give me a second, because I'm just catching up with things on my side. Okay, whoops. Sorry, I am doing stuff on my computer. Okay, got it. So we're looking at this formula now for confidence intervals. And as I just prefaced before, we did inverse norm. Inverse norm gave me the z-score. How are we going to use that when talking about confidence intervals? Here's the formula for confidence intervals, specifically for z values. And that's going to become important later. I'll talk about why. But these are only for z values. What you're seeing here is you have your x bar. That is your sample mean. That would typically be given to you in the problem. You will then notice that we have this notation z. That, in short, is your z-score. So on the previous page, we found our z-scores. This is not a minus sign, it's more like an arrow. We found our z-scores to be a 1.65, 1.96, 2.8. We found those z-scores on the previous page. Those z-scores would be right here in the formula as your z value. We then take those z values and we multiply them by sigma of x, which, yes, that would technically be the population standard deviation. So the beginning examples that we'll look at will be based upon the population standard deviation over the square root of n, and we know that already to be the sample size. Some things to note or put into your notes. The first one is I'd like you to label the z value as the critical value, because a lot of times that's how it's referred to in the book. If they say find the critical value, they're talking about finding the z-score. This whole piece then, okay, the piece that's in the parentheses, and again, these are key vocab words that they might ask you like, hey, find the this, find the that. You have to know what part of the formula they're ultimately talking about. This parentheses section, that's the standard error. Okay, the standard error. Again, we kind of talked about that a little bit before. At that time, we didn't really have the idea of the z-score in there, but now we have the z-score. And then last but not least, so we talked about the x-bar, the z, the standard error. And then if you look for the value of the z times your parentheses, so basically the whole plus or minus part of that, it's going to seem very similar to standard error. You're seeing that error, but now we're going to call it margin of error. So it's a little bit more than just the standard error. It takes into account that z-score, and basically the z-score is kind of what percentage of confidence you want. As you change your confidence level, the z value is the part that's going to change. The standard error, that's kind of, it's exactly that. It's standard, it doesn't change. That's just the natural phenomenon happening. But then you tack on that z-score, which is ultimately your percentage. And now you're kind of saying, hey, how confident are you in this margin of error? You know, how confident are you in this window of space? So let's get into our first example, kind of using this formula here. So we have an example. A psychiatrist is doing a study on teens and their sleep patterns. Prior to the study shows that teens should get 8 hours of sleep. I think we've all heard that before, where they're kind of, this is their hypothetical prediction that teens should be getting 8 hours of sleep with a standard deviation of 1.25. Because that is the prior claim, in theory, you're not going to really need this, but in theory, this would be kind of your mu of x. You don't really need that in this question, but we do need sigma of x. So sigma of x is the 1.25. A recent sample of 15 students, so there's my n, 15, indicates that the mean hours of sleep is actually 6.8. So that's coming from my sample, so we're going to call that x bar. So x bar is 6.8. Calculate a 90% confidence interval and a 99% confidence interval. So once we have all these defined, I would say it's very, beneficial to define all of these. You don't usually have mu of x, so we're just going to focus on these three variables for now. But the next thing we would need to have, according to the formula, we have the x bar, we have sigma of x, we have n, we just need the z. So we would need to find the z. They are asking us to do it twice at the 90 and the 99 marker. So in short, I need to do inverse norm for the 90%. So keep in mind, where would the 90% be? That's going to be at 0.05. And then just make it positive. So don't forget, these have to be positive. For the 99 marker, we technically did calculate that one on, well, we calculated both of these on the previous page for the record. But this would be the inverse norm of 0.005. So again, if you need to flip back, you could see we did both of these and found both of these. The first one, the 90%, would have a z-score of 1.65. and the other one would have a z-score of 2.58, actually kind of coming from up here, the 1.65 and 2.58. So in short, we now have our z values. Let's label these a little bit. We have our sigmas, our n, our x bar, and then we have our z's. And now it would really just be kind of plugging it into this formula to see what we get. So going through these calculations now, colors a little bit, we would be taking our x bar, so that would be 6.8 plus or minus the z-score, so let's do the first one, 1.65, times sigma of x, so that would be a 1.25, over the square root of n. Boom. We calculate that, going through, I would do on your calculator, I'd do 1.25 divided by the square root of 15, find that whole piece, and then times it by the 1.65. Once I times that by 1.65, we should be getting, my numbers are gonna be out. Hold on, let me recalculate it. What I have on my answer key looks like it might be 1 decimal place off, which I don't love. I love to be as exact as possible. So times 1.65, that is going to give us 6.8 plus or minus 0.53. Yeah, that's actually what I had on my, in which at this point, this would be your confidence interval. We would typically, when we go to that interpretation, so think back on the first page, your interpretation usually looks something like this. We are 90, ours would be 90. We are 90% confident that the true population mean lies between blank and blank. You would actually want to take this one step further and actually calculate what that high and low would be. So don't just kind of leave it as plus or minus, take it to those final calculations. So let me run that 0.53 and then do a minus 0.53, and we should be getting 6.27 to 7.33. Okay, so again, that is for the 90% one. I'm gonna highlight that factor, that was the 90%. You should now try it with the 99% confidence interval. What you're going to find when you do the 99% confidence interval is that these numbers, or this range, is going to be a lot bigger. So right now you only have a difference of maybe about 1, as far as your range goes. When you increase your confidence level, you are increasing your interval, right? So right now our interval is pretty small at 90%. There's only, a range of like 1, but when you increase that confidence level, you're going to increase your sample size. And for a quick comparison, here's your difference in them if you run that calculation. So boom, boom. The other one, when you do 99%, you will be going from 5.97 to 7.63. So you can actually see that interval kind of widens when you increase your confidence. Bigger confidence, bigger net. Smaller confidence, smaller net. Smaller confidence, more precise. Bigger confidence, less precise, just for comparison things. Moving on. Some questions you should be aware of and be thinking about when answering some of these. So how sure are we of these results? That is ultimately talking about your percentage. Are you 90% confident? Are you 95% confident? How confident are you of these results? What is our margin of error? Keep in mind, margin of error as predefined up here. Margin of error is basically the whole plus or minus section. So coming down here, our margin of error would be this plus or minus 0.53. You would have had to do the 99%, but in short, margin of error is the plus or minus that number that you got. What effect does sample size on our confidence, have on our confidence? So we have talked about how like increased confidence, decreased precision, increased precision, decreased confidence. But something we haven't talked about is how sample size can actually affect your confidence. thinking back to that formula, your sample size is in the denominator here. So what they're really saying is that if I increase n, what will happen to basically this interval? And in short, and you can write this down, bigger, and I'm sorry, you can see my hand here, bigger sample size means smaller interval. So what this is kind of saying is, let's say that you are 99% confident. You do not want to change your confidence, but you do actually want to become more precise. How can you keep your confidence the same, but become more precise? Bigger sample. The bigger your sample is, the smaller your interval will get, which means the smaller your interval, the more precise you're getting. So if you want to keep your confidence, but become more precise, you're going to have to go bigger sample, in short. Now, here is that sentence we had before, if you wanted to try it out. Basically, the sentence will always go, and this is one of those ones actually on your hot pink piece of paper, one of those sentences you just have to have memorized for the AP exam. But in short, it goes, we are 95% confident, or 90%, or 99% confident that the true population, now we usually don't say parameter for the record, you should actually be using the word like mean. We're going to eventually talk about proportions. So sometimes you'll say the true population proportion, but right now we're just doing mean. So it'd be, I'm 95% confident that the true population mean is between this, and then you'd actually find those two values. Now, jumping back, blink, blink. I told you I'm going to be jumping around a lot. Oh, where'd it go? Sorry. Did I fix it? I think I fixed it. Yeah. Okay. I know we're a little bit ahead of this. Okay. So confidence, going through that in all possible. Okay. So talking about confidence a little bit, I told you how this confidence is going to be a little bit different than standard. So we do talk about confidence in like, hey, how confident are you that these results are going to be good? And naturally, a lot of times you would be like, oh, well, you should be very confident. You should be 99% confident. And that idea of a higher percentage is true. Like, obviously, you want to be more confident, but what are you actually being confident in? So there's this idea that when you are talking about the confidence level, you're not just, this is not just kind of a figure of your imagination where you're saying, yeah, I'm pretty confident. There's actually a reason that you get these confidence levels, and kind of the meaning behind why you would do 90% confidence versus 99% confidence. And ultimately what a confidence level is saying, and you can see it right here, in all possible samples of size n, the true population mean will be contained in 95% of the intervals generated. Now, keep in mind, when we're doing an interval, you are basing it upon your single sample. So if I was to run the study again, keeping at a 95% confidence level, my X bar might change from sample to sample, which means I'm getting a buttload of different intervals. So look at this picture for a second, don't read it. But see these blue lines? These blue lines represent a confidence interval. Now, this first blue line that you're seeing here, okay, on the far left, first blue line, that would be like me going through, getting my X bar, and then doing my plus or minus. Then let's say I go to the second blue one. So on the second blue one, I look at this and I kind of say, okay, well, this was the same confidence level, 95% confidence level. My plus or minuses were all exactly the same, but now I have a different sample with a different X bar, and this is what's generated. And if you think about it, every single time you do a different sample, you're getting a different X bar, which is ultimately going to give you a different interval. So all of these blue things that you're seeing are different intervals. So each of these blues, these are different intervals generated, each of them having a different X bar. In theory, their margin of errors would be the same. I think I said that right. The margin of error, yeah. Their margin of error would be the same because their n should be the same. The sigma of x should be the same. your z-score, your confidence interval, should be the same. So the margin of errors are actually all the same. What is changing is the X bar. And every single time you get a different X bar is going to slightly change what your interval actually encompasses. So that low number to that high number changes depending on the X bar. Now, notice that one of these is in red, okay? What that one is saying is that I did everything right. I went through, there's my X bar, there's my margin of error. But one of these intervals does not actually capture mu. Now, we don't typically know what mu is. It's kind of a hypothetical situation. But in short, when I say that I am 95% confident, you're not saying that, you know, hey, trust my results. These results are good. I'm 95% confident. And on top of that, I'm not saying that that interval is perfect. And I'm not really saying that that interval I am 95% confident in. You are saying that you are 95% confident in all these intervals. 95 of those intervals will capture the true mean. So one of those intervals will not capture the true mean. Is the interval you calculated that one interval? Maybe. You don't know, which is why you're saying you're 95% confident in the interval. You're 95% confident that this is one of those 95% intervals, but it is slightly different. And I really want to emphasize that, because when you go to your interpretations and you're thinking to yourself, we are 95% confident that the truth, if you try to change that wording at all, and you are saying, I am 95% confident in this interval or anything, you're digging yourself a hole, because that's not what it means. It means that out of all possible intervals, 95% of those intervals will capture the true population mean. And these numbers are one of those possible intervals. And we're hoping that this interval will capture the true mean. But as you can see, sometimes there's intervals out there that don't capture it. And we just genuinely don't know if our sample is that or not. We hope it's not, but it obviously could be. So long story short, make sure you are sticking with that sentence structure and not varying too much. And I'm sorry, I know I'm on the long side, so feel free to pause the video and come back to it later. I'm gonna keep going, okay? We're on roll. So there's a couple more pieces with this idea of confidence intervals that come into play. Some of these I'm gonna glance over because we've talked about them. There are some conditions that have to be met for a Z confidence interval. These all sound very familiar to you. Randomness, you know, it usually just says that in the problem. Approximately normal, you're looking for your n to be greater than or equal to 30, or your population could possibly be normal. Independence, that's the same 10% rule we saw in the last unit. And then this idea that the population standard deviation is typically given to you. Now, what if sigma of x is not given to you, right? And you're looking back and you're like, oh, sigma of x is given to you in the problem. What if sigma of x is not given to you in the problem? We run into this issue then, and then we're like, hey, wait a second. Looking back at that formula, there. Looking back at this formula, I need sigma of x. So what if you don't have sigma of x? What do you do then? So this takes us to our kind of last point of today, T confidence intervals. And I'm so excited for T. So we've dwelled a lot in Z scores and Z distributions, and now we finally get to do T distributions. And if you've ever explored your calculator and seen inverse T or TCDFs, this is kind of the direction that we would be going here. So again, pause the video if you want. I know I'm going long, and this is actually kind of like the second half. So maybe you want to come back to this one later and kind of like finish up Z scores and be like, hey, I'll do T's for homework tonight. So if you want to pause the video, it's totally fine, but we are going to go into T distributions now. So for T distributions, let me find where I am right now. Sorry. It says we rarely know what the population standard deviation is. So T intervals kind of make sense. We're going to need them. Just again, Z's are great, but Z's really only work when you're given that population standard deviation. T's is a lot more common. You might actually have, and let me say this, T focuses on samples. So Z is from the population, T is from samples. So a lot of times you will be able to have a sample distribution, but you might not have the population distribution. Now, overall, what's the difference between Z's and T's? They're really not that different. They both have the idea of critical values, but what the critical value actually is, you know, because think about it, the critical value was your Z-score. Your Z-score is going to change, and it's now going to be a T-score. The other key part of a T-score is that we're going to have to account for something called the degrees of freedom. And we're going to see how this comes into play here in a second. But degrees of freedom is ultimately n minus 1. Now, we should be familiar with what n is. N is your sample size. But in short, it kind of plays a role that you'll need the degrees of freedom in a lot of these formulas that we're going to see here. Now, to just give you a quick visual here of where a T distribution falls or what it looks like, you have your Z distribution in blue. That's a pretty beautiful, nice, tight, normal curve. The T distribution, a little bit shorter and a little bit more spread out. It's typically not as accurate because it is based upon a sample rather than the population. So you're going to lose some of that accuracy, but sometimes that's the best that you have. Here's the formula for the T confidence interval. It does look a lot alike. So you got that X bar. Here's that T score. So again, we talk about the Z score versus a T score. This one would be the T score. The other key difference you should be noticing is S of X. So rather than sigma of X, we have S of X. S of X, you saw it popping up in your calculators at the beginning of the year. That is the standard deviation for your sample. So when you actually have a list of values, you're able to plug those lists into your calculator, run the one vars on your calculator, and find S of X for that standard deviation of the first one. So the difference here in the steps, not huge difference. You will be calculating critical value, but rather than a Z, you'll be doing a T. The interpretation as far as I am 95% confidence is the same. The assumptions pretty much are all the same. We'll see assumptions coming up here in a second. So here's the assumptions: random, check; approximately normal, the same; independent, the same. The only one that changes is that you would need your sample standard deviation because the population standard deviation is unknown. So that's pretty much the only difference, is you need S of X. So let's practice some of these calculations. And I told you I'd be jumping around a bit. So let's hop back here. Okay. So let's practice some of these calculations and see these in works. And I'm very excited for this slide. I'm trying to convey my statement. Okay, so T intervals. So we want to ultimately find the T value here. We're trying to find these critical values. We did critical values before. On a side note, if you want the Z, we'll just write critical value. If you want the Z critical value, that's when you do inverse norm. If you want the T critical value, you're going to use inverse T. And I have a lot of papers everywhere and I totally lost my calculator. Okay, I found it. So what I'm talking about is if you go on your calculator, we would go second vars. And I know you're not gonna be able to see it much, but follow along on your calculator if you can. We have the one, if you scroll down to number 3, it's inverse norm. Look right below inverse norm and you're going to see inverse T. And I'm trying to think if I can make that. You can kind of see it. It's a little blurry, but you do see that you have inverse T. So when you are doing a T interval and you recognize it as a sample, like, hey, this is a sample, I'm doing a T interval. That's the button you in short want to use. So we're going to be using inverse T. So for this first one, T interval, I'm going to go inverse T. When you're doing an inverse T, the first step you should do is find that critical value. So think of it like, where's the paper I'm thinking of? Here. So think back when we did here, and we would do like inverse, and then we plug in that decimal. We want to do that here, but small word of advice. For these ones, we were pretty good at like just recognizing that it should be positive. Here, you're not going to really want to do that as much. You want to be pretty accurate. So I'm sorry, going back here one more time. So we would do inverse norm of 0.05. You would get a negative and just flip it to positive. For inverse ones, and I'm just kind of processing a thought. Actually, yeah, okay, cool. So for inverse ones, you can actually do the same concept as well, as far as the positives to negatives go. So this one, we had a 98%. So I'm going to do inverse norm of 0.01, because again, be thinking your bell curve, 98%, if I'm going to go 98%, 98% is going to give me 1% on both sides. So if I run inverse t of 1%, we should be good. Now the difference is when you do inverse norm, that would be all you would do. You would hit enter. Give it a try on your calculator. So you go inverse t, you type in 0.01, you hit enter. It's going to say argument or error. And here's why. Inverse t's, unlike inverse norms, actually have to have, so I'm going to put, hopefully you'll know what I mean, like kind of percentage there, has to have the degrees of freedom. Now, if you remember, I defined the degrees of freedom on the previous slide. Degrees of freedom is n minus 1. So not only do I put 0.01, but I also have to include degrees of freedom. So my degrees of freedom here would actually be 11, because n is 12, so degrees of freedom would be 1. When I run that on my calculator, what I will get is a negative, but remember, I want the other side, so I'm going to go positive, 2.72. That is your T critical value. And in that formula we were seeing previously, I don't have it printed out, I'm sorry, but in the PowerPoint slide, you need that T value. This is the T value. Inverse norm, that's the Z value. This is the T value. Okay, so these are the T values. Now I'm going to do a couple more. I'm going to pick up the pace a little bit here. So the next one would be inverse T. This is 95%, so that would be 2.5 on either side. I'm going to do 0.025 degrees of freedom, 21, not 22. It will give you a different answer if you accidentally do 22, and it would be a wrong answer, so be very careful of that. That's going to give you a 2.81. Now I threw in a Z here just to switch it up for your notes purposes. Reminder that Z's you should be doing inverse norm. And when you do inverse norm, 0.025, these are both 95%. So both 95%, both of them should be a 0.025, 0.025. But with inverse norm, you don't include anything after that. So seeing these side by side was kind of the point here. When I do inverse norm, I'm going to get a 1.96. And so noticing that there are slightly different values between an inverse T and an inverse norm. Inverse norm, 0.025 only. This one would be 0.025 plus degrees of freedom. So T always needs that degrees of freedom. Now, I do also want to emphasize that there are other ways you can write some of these. So for this one, when you do your inverse T, and you're thinking to yourself, 90%, so 0.05 comma 61. You could also do inverse T and do 0.95, because by doing 0.95, that will give you the positive result. So when you just do 0.05, that typically gives you a negative number, and we just have to think about it being positive. But if you actually do, rather than doing the 0.05, you would do the 0.95, will give you that positive one. So I'm trying to progress things here because I know the video is getting long. One more piece here that I want to kind of dive into, and then we might be wrapping it up here in a second. But some other cool things that I think can happen when doing these critical values. Something you might also be thinking about is when we did normal CDF. So I know it doesn't always like to show you guys my calculators. But if we go normal CDF, oh, there we go. So we've done normal CDF before. Think about when we've done normal CDF. Normal CDF would be in a situation like this, where we want to find where it's greater than a certain value. So this would be normal CDF. we would want greater than, so I would do 1.5, that's your z-score, comma infinity, and then run that calculation. So 1.55 comma infinity, boom. And what that does is it gives you your p-value, or sometimes we call that your percentage. We get 0.06 or 6%. For z values, you don't even really need the ends. Because think about it up here with inverse norm. You didn't need n for inverse norm. You don't need n for normal CDF. So really having those ends is just extra information. Even when I look at the second one here, okay, in the second one, I would do normal CDF, negative 1.5 to 1.5, you get those p-values. Fun fact, if you saw on your calculators, because again, you're glancing at your calculators and stuff like that, what you'll notice is on your calculators, number 5 and 6, there's a T-PDF and a T-CDF. Similar concept here, T-CDF. So we have normal CDF, we have T-CDF. T-CDF would be the same idea. I want a t-value greater than 1.5, T-CDF, 1.5 comma infinity, but same concept as up here. Inverse norm, you just give the percentage. Inverse T, you do the percent and the degrees of freedom. Down here, same idea. Z, infinity, right? Similar, but now we have degrees of freedom. So in short, T values, you always need to be addressing degrees of freedom. Whether you're doing, inverse T or here doing T-CDF, you always address degrees of freedom. Now, the very last part, or the very last slide that I wanted to hit, to grab this real quick. So we talked about that. Sorry, we're way further down. We've done a lot of this. We're doing good, I promise. So I did this, I went here. Oh, I realized I skipped over something called the panic. Panic is what we're going to be doing tomorrow. So when you are doing a lot of these problems, so right now I've just dwelled on kind of the calculations in a sense, but tomorrow, I think it's tomorrow, you guys will be watching another video. I promise it'll be a shorter video, where I'm going to introduce 2 official examples of all these. So right now we've gotten the background for how to do these calculations, and then tomorrow we're actually going to do 2 samples. But in those samples, in short, anytime they're asking you to assess or create a confidence interval, you're going to do panic. You need to find the parameter to be estimated. We'll talk about that. You'll have to address all the assumptions. The N is to name the formula or the type of interval, so T interval or Z interval. I would be to actually calculate the interval, and then C is to draw your conclusions. Your conclusions are usually that I am 95% confident, blah, 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 blah. So we will dive into panic more tomorrow, and that's totally fine. The last part, following through these PowerPoints. Oh man, I really actually wanted to do this one, sample size from formulas. I have that one printed out. Oh, I didn't print that one out. Sorry, I printed out all the ones I wanted to talk about, but I realized I did not print that one out. So let me just show you these ones and talk about these a little bit, and then we'll be done. So the last ones here, I'm just kind of showing you guys my answer key here, is there are some times where they will ask you to find the sample size. So if you're looking at this formula for the margin of error, okay, so here's your margin of error. If I'm looking at my margin of error, I usually take the t times the standard deviation over the square root of n. But what if you didn't know n? So we come down here and say, okay, what if they asked us to find the sample size? We're going to take that formula for the margin of error. Now this one, it says z, you can also do it with t, but we'll take that z sigma of x over the square root of n, and you kind of work it backwards to find n. So going through and kind of multiplying that over, I just kind of did the algebraic process to get n by itself. But if we look over here at the final example, so finding sample size in short, you could ultimately take these values. So let me just cover this up for a second. You got the margin of error, and I'm writing down this formula over here. The margin of error, z-score, sigma of x over the square root of n. Let's say I plug in what I know. So it says how large of a sample is necessary to estimate the true mean to within 4 ounces. So within 4 ounces basically means 4 above or 4 below. So you'll see here I said E, that's the margin of error. E would be 4. With a 99% confidence. So that 99%, what that's going to do is that's going to tell me sigma. So E was 4. Oh, sorry. I said sigma. I was getting ahead of myself. The 99% is going to give me the z-score. So my z-score, I could run that 2.58. Finding the z-score just like you would before, inverse norm, inverse t, whatever. You actually, sorry, getting ahead. You actually cannot do inverse t for this because you don't have degrees of freedom. So if you remember inverse t, you have to have degrees of freedom. We don't have that. So this does always have to be a z-score. You're always going to have to do it as a z. And then it says standard deviation is 8. So my standard deviation would be 8. So going through this formula, E was 4, Z is 2.58. I found the 2.58 by doing inverse norm and then 0.005. Okay, just for anyone wondering. So I get that 2.58 times 8 over the square root of n. And in short, from that point, you solve it. So I would take these two, multiply them together. So let's see, that's going to give me 2.58 times 8. So I get myself 20.64. I would then take this square root of n and multiply it to the other side. I would also divide both sides by 4. So algebraically, I'm skipping some steps. If I lost you, then in short, do it yourself. Solve it algebraically without me. We're now at the square root of n equals that 5. Square both sides, and you get n equals 26.625. And in short, what that's kind of saying. Oh, sorry, I was looking at my answer. I was like, oh my gosh, that's not even right. In short, what that's saying is this would have to be your sample size. It'd have to be at least 26.6. If we are talking about, I don't even remember whether this was about healthcare, birth weights, this would be how many babies you would need. You would in short need to round that to 27 for the number of babies. But I think I've taken up enough of your time for today. Hopefully you took an intermission halfway through that. That was like a whole class period long video. It was technically 2 days of notes, so that's why it was a little bit longer of a video. Hashtag sorry, but this is why I didn't give you homework tonight other than to finish filling in your notes. Tomorrow you will have another video. I promise it'll be much shorter, but we will be doing some panic if you're not already panicking. So yeah, that's it.